Hello, welcome to the 2022 AS Computer Science Paper 2 walkthrough. In this video, I'm going to be going over some of the key points which you should be thinking about on each question. This is not a comprehensive walkthrough, so in the real exam you should probably write a bit more on each question, but these are just some of the key points which you should be thinking about.
Okay, cool. So question 1. Describe the difference between natural numbers and integers. So a key point that you want to put down is that natural numbers are positive numbers. Now, depending on your domain, mathematicians don't include zero, computer scientists do include zero, but they are positive, right? And the integers include negative numbers. And then give one example of a number that is an integer but not a natural number. So any negative integer, really. So minus 2, minus 111, minus 93. Cool. 1.2, right. Describe what it means for a number to be irrational. So a rational number is a number that cannot be written as a fraction. So for example, pi e root 71, for example, these cannot be written as a fraction, so therefore irrational. Right, 1.3. Cool. Shade 1 in the counting column to indicate which set of numbers is most suitable for counting, and 1 in the measuring to indicate which set of numbers is most suitable for measuring real-world quantities. Right, so when we're counting, we are counting something. So we're not looking at negative, we're not looking at fractional, we are counting things. So for the counting, I would put integer. And for measuring, now we might be measuring, for example, values which are fractional. So for that, I would probably say real. Right. Okay, question 2.1. Convert the decimal number 177 into unsigned binary using 8 bits. So the first thing I do is write out 8 bits. So 1, 2, 4, 8, 16, 32, 64, and 128. And now I would assign ones to the biggest to the smallest to make that number. So 1, 0, because that would go too far over. 1, 1, and then we need 1 finally to finish, so we end up with that. So we have 1, 0, 1, 1, 0, 0, 0, 1. And that's our answer. Right, 2.2. Convert the decimal number 193 to hexadecimal. So we remember that hexadecimal was split into 16, 1, 16, 0. We shouldn't need more than that, but if we need 16 squared, no, we shouldn't need that. So the first thing I would do is divide 193 by 16, which, taking the integer part, gets us 12. Now we remember that A is 10, B is 11, and C is 12. So we're going to put a C here, and then whatever is left, we're going to put in 16 to the power of 0 column, which is just the ones, right? We only need 1, so we're just going to end out with C1, and that is our answer. Cool. So question 3. State in decimal the lowest and highest values that could be represented in unsigned binary when using 16 bits. So, keyword unsigned. We're not going to have negative numbers in this, so the lowest value we can get is all zeros, meaning 0 is our lowest answer, right? So 0. So our highest value is going to be 2 to the power of 16 minus 1. Now, to give a concrete example of this, let's assume we have 3 bits, right? And we're going to set them all to 1. Now, this is going to equal 7 in decimal, but if we use 2 to the 3, that is going to be 8. So in general, we're always going to want to say 2 to the n minus 1 for the maximum number in unsigned. Okay, so question 3.2, binary multiplication. So the simplest way of going about this is if we start this end, we want to multiply this 1 by all the ones and zeros on the top layer, right? So for that, we're just going to get the same thing, 0, 0, 0, 1, 0, 1, 0, 1. Now for the next one, which is this one, we're going to add a 0 here, right? And from that 0, we are then going to basically just shift along the prior answer we got by 1 because it's the same thing multiplying by 1. So this time we're going to have 0, 0, 1, 0, 1, 0, 1, right? And then the same for the final one as well. We're going to add 2 zeros this time, but we're just going to shift along all the values 1 to the left, like that. So now, finally, we just want to add up all the values, and that should attain us a value of 1, 0, 0, 1, 0, 0, 1, 1, right? And that's our final sort of value. Right. Question 4.1. ASCII is a one-character coding system. Explain the term character code. So a character code is a unique number given to represent a specific character. So when you type on your keyboard, the operating system needs to know which key has been typed, and we can't have clashing values, so we use a unique number for each character. 4.2. Why was Unicode introduced as an alternative to ASCII? Well, Unicode is introduced to support a larger range of characters, right? So introduced to support a larger range of characters. And that's because due to, more symbols coming in, you've got things like emojis or mathematical representations which you need to represent. So that's primarily the reason. So 4.3, explain how the parity bit would be generated for the character code in figure 3 using even parity. So simple answer, number of ones summed. If the total is even, then the parity bit is 0. Otherwise, set to 1. And that's the simplest way of probably explaining that 2-mark question. Right, 4.4, write the parity bit below to complete the byte that will be sent using even parity. So we know that number of ones must be even, so we're just going to set a 0 there because we have 4 ones. Okay, question 5. Describe the difference between analog and digital data. Well, analog data is continuous, right? So it can take data in some given range. It can be fractional. It can be anything, right? Digital data is discrete. So we can say that it can be stored as binary. It can yeah. Okay, 5.2. Describe the steps that an analog to digital converter carries out when converting a sound signal. So the ADC, first of all, is going to take samples. ADC will take samples at given intervals, right? And then the next stage is that these samples are quantized, which means that the amplitude is measured at these given intervals. So to give an example, let's assume we have this and our sampling rates is like this, right? So at each sample, their values are going to be quantized, and the amplitude will be read. And at each sample, a binary value is given. And that is how we go from analog to digital. All right, question 6. Define the term software. So software is a name given to programs or code that is executed. For example, simple one mark. 6.2. Translators are one type of system software. Give two other types of system software. Um, so this could be, an operating system. This could be libraries. This could be utility programs. Anything from those. Okay, 6.3. Some compilers translate source code into an intermediate language rather than producing an executable file. Bytecode is one of those examples of an intermediate language. Explain how this code is used after it's been generated. So, first point, software is needed to finish this process, right? So we would need some sort of virtual machine, maybe, or some sort of compiler to convert it into the machine code for the specific processor that the code is running on. 6.4. Give one reason why some compilers produce their final output in an intermediate language instead of machine code. So this one, you only need to, well, the compiler only needs to translate source code once. Um, and in addition, it's more portable, or you could use it for cross-platform because you're not compiling on one specific machine. Okay, so question 7.1. State which logic gate has the truth table shown in figure 4. Well, the simplest way of doing this is, to be honest, trial and error, right? So 0, 0 is going to be 1 and the rest are zeros. So from this, you can hopefully see that it's a NOR gate, right? Because when you OR it, all of these will be 1 and this will be 0. However, it's the opposite in this case, so it's most likely a NOR gate, right? Question 7.2. State the logic gate that's stated by the symbol shown in figure 5. So this is a NAND gate, and that is because of this little circle at the end of what looks like a D. That's how you show it. So NAND gate, if it was a normal AND gate, it would just look like that. Cool, so draw the logic circuit for the following Boolean expression. Well, we've got not A dot B plus, or C, right? So, and that's all being knotted. So, the first thing we can do is I would work from this side, right to left. So you've got the C and you know it's being knotted and ORed by the other expressions. So we're going to have a NOR gate, first of all, which is going to look a little something like that. So that's this part done. And then we need to go A and B all knotted. So we know that's a NAND gate. We know that we saw that in the prior question. So that is just going to be like this, small circle on the end. We're going to connect that up and then we're going to put that to Q. Right, and that's our not particularly well drawn logic circuit. Cool. Question 7.4, complete the truth table below. So not B, first column, is just going to be the inverse of the B column, so 1, 0, 1, 0. A or not B, so this column and this column are simply going to be 1, 0, 1, 1. And then this column and it together is going to be 0, 0, 0, 1. Because when we have an AND, they both have to be 1 for it to be 1. And then the final part, using the final column, give a simplified Boolean expression for A or not B dot B. So that's this column here. If we look at the two inputs, it's fairly simple to see that it's actually an AND gate. So what we can say is just A dot B. And that's because when both of these inputs are 1, we have a 1, and the rest are 0, which falls in line with an AND gate.
Okay, so question 7.5. Using the rules and identities of Boolean algebra, simplify the following Boolean expression. Now, the first thing I'd go about is looking at the right-hand side, right? Because we've got two knots on there, and we want to try and, we know that we can simplify that using De Morgan. So starting that off, we have A plus B naught dot. Now, doing De Morgan on this would give A dot B naught, like that. In brackets, I'd probably say what I'm doing as well. So De Morgan there. Okay, cool. So the next stage is we have an and we have an or in this bit here. So probably to use the multiplication rule, right? So this would yield A dot B naught plus B naught dot A dot B naught. Let's just put multiplication. Okay, cool. So now we can actually see in this that we have two of the same here and two of the same here. So we can use the rule x dot x equals x. And that would give A dot B naught plus A dot B naught. So now we can use the rule x plus x just equals x. And that's just going to give A dot B naught. And that's our answer.
Okay, so number 8 is to do with the fetch execute cycle. And 8.1 is asking us to indicate the order at which the events occur in the table. All right, so the first one is going to be B, because the program counter holds the memory address of the next instruction to be executed, and then it has to put that on the memory address register, right? So that makes sense for the first one, okay? The next one is that we're gonna go to A, where it says the contents of the memory buffer register are copied onto the current instruction register, right? So we need to take that instruction in the buffer and we need to copy it into the current instruction register so the CPU knows which instruction to execute next, okay? The third one is going to be C. So the control unit decodes the contents of the current instruction register. So the CPU needs to know what it is to do, what it is to execute. So the control unit decodes that instruction. And then finally, we're going to store the result of the calculation. That is going to be D. So that's your order. Okay, so question 8.2, describe the role of main memory in the execution of computer programs. So main memory stores the programs, it stores the instructions to be executed. To be executed. Additionally, it also might store any sort of values or data resulting from the running. So it stores values or data. And it also may return the data stored in a particular memory location for pointers, for example, right? All right, 8.3. All right, 8.3. State the name of the processor component that is responsible for performing mathematical operations such as addition and multiplication. So that is the ALU, or the arithmetic logic unit. So explain why increasing the data bus width can lead to improvements in processor performance, or simply that it increases the amount of data which can be transferred. as if you have a larger width, you can transfer more bits at once, making it potentially faster. Okay, 8.5. Identify the bus that would need to be changed and state the change needed so that the maximum amount of memory addressable would be doubled, right? So we would use the address bus, so that's what we need to change, and we need to increase the width by 1. And this is because if we, for example, have a string of, so the amount of addressable memory is 2 to the n. So if we have a width of 1, we're going to have 2 to the 1. If we're going to have a width of 2, we're going to have 2 to the 2. So, for example, that would be 2, that would be 4, and one more example, that would be 8. So all we need to do is increase that width by 1. Okay, question 9.1, shade 1 to show which of the assembly instructions in figure 7 uses immediate addressing. So immediate addressing is where you use the direct value and not something stored in another memory location or another register. So that is going to be B, because it is the only one which uses number 42 and not memory location 42, which A does. Okay, so question 9.2. A computer program is required that will multiply the value stored in X by 2 if it is less than 50 and leave it unchanged if it is 50 or more. The algorithm for this task can be written in pseudocode as if X is less than 50, then X is X times 2, and if. So we need to write an assembly language program using the AQA assembly language instruction set to carry out this task. And at the start, X is stored in memory location 101, so that gives some indication as to how to start. Right, so we need to load into some register R1, I'm going to call it. Doesn't have to be, it could be R, 1000, but just for simplicity, we call it R1, and from memory location 101. Then we want to come over to the pseudocode and compare R1 to the value of 50. If we have the value which is greater than, then we want to move to some end, right? So we want stop. We'll call it end for now. And also, if we have a value which is equal to, then we also want to end, right? So what do we want to do if we have the value less than 50? Well, we want to multiply it by 2. And the easiest way to do that is do a simple logical shift left to the value in R1, and then store it in R1, and then to the value in R1 by 1. So, for example, if we have the bit 1, 0, that's going to be value 1. If we shift it to the left by 1, we're going to have 0, 1, 0, which is 2. So that simply doubles it, right? And what do we want to do? We want to store that value from R1 back into memory location 101. And then we also need this branch end. We'll call it end, and then we can halt here. Cool. Okay, right. Question 10, last question. Describe the purpose of the start and stop bits in asynchronous data transfer. So, asynchronous data transfer, the start bit is going to wake up the receiver. So whoever's receiving the bit, we want to wake them up, right? The purpose of the stop bit is to allow the next start bit to be recognized, right? So we need a way of determining which is a start, which is a data bit, and which is an end bit. Otherwise, we'd have this continuous stream of reading data and never knowing which is coming from where or what data is what. So it'd be very mixed, it would get corrupted very quickly. So we need that stop bit. Okay, 10.2. Define the term protocol. Well, a protocol is a set of rules, sort of governing the communication between devices. So how they do that, right? define the term latency. So latency is the delay between an action being initiated and you observing that effect, so it taking place, right? A good example of that might be on games. So network latency. So when you press A on a controller, how long does it take for that action to be observable? That's what you would call latency. Cool. Okay, 10.4. Final question. Explain how a physical star topology can behave logically as a bus network. Fairly straightforward. You can use a bus transmission protocol, and then we would need to use the appropriate switching, which creates a switch which would create temporary buses between two nodes. So I guess you use appropriate switching, something along those lines, right?